Hey, it's Mr. H, and in this video I'm going to show you the link between antiderivatives and the area under a curve. So let's go. Let's start by looking at the area under a curve. So if I draw a curve here, it doesn't really matter what that function is, but what matters is that I want to look at the area under that function. So let's call this function here with our y-axis, we'll call this y equals f of x. But we're also going to have another function in this picture. It's going to be the area function. Let's call that area function a of x. So you could picture as we go over on the x-axis a little bit further, we're going to have the area change. The area is going to increase in this picture. So let's do that next. If I add just a little bit more area over here, then let's look at what's going to happen. Well, by a little bit of area, I'm going to call that a distance of h that I have added in. So now I am on the x-axis at a spot that we'll call x plus h. And the area that I have overall, the entire area under the curve, is now the area of x plus h in my function. So here's the interesting idea. If I look at just the area of this portion that's been added in, let's make an expression for that. Well, it's going to be the full area, a of x plus h, minus the area that I began with, a of x. Now that's an interesting expression. It's beginning to look a little bit like our limit formula for derivatives. If we were to write down the limit formula for derivatives here real quick, with an f of x plus h minus f of x over h, we'll notice that we have a function evaluated at x plus h minus the same function evaluated at x, but then we're dividing that by h. So here's how we can build that same type of situation with our area function. Let's look at just the portion of the graph that was in red, because this portion of the graph was written as area of x plus h minus the area of x. That's the total area of that region that I have in red. But notice that it's not a rectangle, but it's almost a rectangle. I could approximate this by cutting it off like this and looking at the area of this rectangle, where I have h as the width and I have f of x as the height. Now as I approximate that area, I would just do the length times width. I would get f of x times h. So let's say that this area is approximately f of x times h. Now what's going to happen as h goes to 0? That's the interesting thing. As h gets smaller and smaller, we're going to have a closer and closer approximation to that area. So what this equation gives rise to is that we can divide by h on both sides, just like we expected, and then take the limit as h approaches 0. And notice what we're going to have is that f of x equals the limit as h approaches 0 of a of x plus h minus a of x over h. And on the right side there, all of this would just be the derivative of a with respect to x. And on the left side, we have the top border of that area. Now this is an extremely important function. F of x equals the derivative of the area under f of x. So when we turn that around, that would mean that the area is the antiderivative of the border function that is at the top. The way that we write this is the area equals the antiderivative of the border function that is at the top, where this simply means antiderivative. I hope that this helps as an introduction to where the antiderivative, the integral sign, and the link between the area under a curve and the antiderivative all comes from. If you're interested in seeing more like this, just comment below with what you'd like to see.